Hello everyone, my name is Fuzuli Akcay and I work at Istanbul Technical University. The research I am to present was conducted at the University of Central Florida during my visit in 2019. The presentation covers our study on the strength of 3D printed aluminum micro-lattice structures. This research consists of two parts: theoretical development and numerical investigation. However, I will present a brief overview of experimental work as well. Experimental work was conducted by Professor Wu's and Professor Bai's research groups and published recently. At first, let me start with a quick definition of lattice structures and the objective of the current study. A lattice structure is a type of cellular structure which has a repeating structure of a unit cell. The unit cell consists of interconnected struts and nodes in three-dimensional space. Although conventional manufacturing processes of lattice structures in advanced applications are complex, inefficient and expensive, additive manufacturing overcomes these difficulties. Additively manufactured lattice structures are used in various engineering applications, particularly in aerospace and automotive industries, as well as biomedical applications, due to their high strength-to-weight ratio and excellent energy absorption capacities. A traditional way to examine the response of lattice structures subjected to external loading is to perform experimental research and or to employ numerical investigation. In other words, a theoretical model to analytically determine the strength of micro-lattice structures is lacking. Therefore, the objective of the current study is to develop a theoretical model and verify the model through existing experimental results and finite element simulations. Experimental work was conducted by Professor Wu's and Professor Bai's research groups and published recently. 6 different unit cell configurations were utilized in the experiments: cubic vertex centroid, cubic diamond, cubic fluoride, tetrahedral octahedral edge, tetrahedral octahedral vertex centroid, and tetrahedral vertex centroid. 4 micro-lattices with different number of unit cells and different strut diameters were fabricated. That is, 24 aluminum, silicon, magnesium micro-lattices were designed. Cubic vertex centroid and tetrahedral vertex centroid unit cell configurations are of particular interest of this research, as these two cases are the simplest geometrical cases to consider in theoretical development. 2 products from these particular designs can be seen at the right part of the slide. The one at the top shows a fabricated structure utilizing a cubic vertex centroid unit cell model, and the one at the bottom shows a fabricated structure utilizing tetrahedral vertex centroid unit cell model. The analytical model is developed utilizing limit analysis. The model is based on 8-beam model with each beam developing a plastic hinge. Plastic hinges develop at locations where the largest bending moments are experienced. Half a cube within the unit cell is considered in derivation to avoid plastic hinges at intersections of the struts, and normal force distribution is neglected. The free body diagram is shown on the right-hand side of the slide. Here, F represents total applied load, delta, displacement of a beam, mu, full plastic moment, L, length of a beam in half cube model, and theta 0, angle between a strut and horizontal plane. The virtual work can be determined as 2 times F cosine theta delta dot. On the other hand, the absorbed work at collapse in the plastic hinge is equal to amount of hinge rotation times plastic moment. Therefore, the absorbed work equals 8 mu delta dot over L, as the amount of rotation is calculated as delta dot over L, and contribution comes from 8 beams. Therefore, the equality reaches F times cosine theta delta dot equals 4 mu delta dot over L. Here L, which equals half the strut length in half cube model, and cosine theta can be determined as a times square root of 4 and square root of a times square root of 3 over 4 and square root of 2 over 3 respectively, where a represents the size of a cell in each principal direction. Here we would like to remind that full plastic moment depends on the shape of the cross section. Full plastic moment of a circular cross section is 4 times sigma y r cube divided by 3, where sigma y is the yield strength and r is the radius of a strut. Finally, substituting these expressions here yields a collapse load of 64 sigma y r cube divided by 3a square root of 3 times cosine theta 0. The strength can be obtained by dividing the force over area, and substitution of the collapse load, which was derived in the previous slide, into force yields the strength of cubic vertex centroid lattice. And this expression is displayed here in red color. Total area occupied by the struts over the volume provides relative density of the lattice. Here we would like to point out that the ratio between the lattice strength and the yield strength yields 1.5 power of the relative density, which is consistent with the experimental results. For aluminum, silicon, magnesium microlattices were fabricated by selective laser melting for this specific unit cell configuration. Sample number 1, sample number 2 consist of 8 cells by 8 cells by 8 cells with 0.4 and 0.5 millimeter strut diameters respectively. Similarly, sample number 3 and sample number 4 consist of 10 cells by 10 cells by 10 cells with 0.4 and 0.5 millimeter strut diameters respectively. Experimental strengths were determined by dividing the compression load displacement data over the cross-sectional footprint area of the microlattices and the initial dimension of the specimens. The table at the bottom compares experimentally and analytically obtained lattice strengths. Here we utilize the yield strength of 460 megapascal for analytical determination, since 460 megapascal corresponds to compressive strength of bulk aluminum silicon magnesium alloy. As can be seen from the table, the maximum absolute relative error in analytical results is on the order of 20%, which we believe is reasonable. Similar to cubic vertex centroid model, that vertex centroid model is based on 4-beam model, and again half a cube within the unit cell is considered in the derivation. The free body diagram is shown on the right hand side of the slide. The virtual work can be determined as 2 times F times cosine theta delta dot. On the other hand, the absorbed work at collapse equals 4 times mu times delta dot over L, as the contribution comes from 4 beams in this case. Here, L, which equals to half the strand length in half cube model, and cosine theta and full plastic moment of the cross section are the same as the ones for cubic centroid case, cubic vertex centroid case. Hence, substituting these expressions into the equality yields a collapse load of 32 sigma y r cube divided by 3a square root of 3 cosine theta 0. The strength can be obtained by dividing the force over area. And the substitution of the collapse load into the force yields the strength of that vertex centroid lattice, and the expression is displayed here in red color. Please note that the ratio between the lattice strength and the yield strength is 1/2 power of the relative density for that vertex centroid as well. And this is consistent with the experimental results. Here again, for aluminum, silicon, magnesium microlattices were fabricated for that vertex centroid cell configuration. Sample number 21 and sample number 22 consist of 8 cells by 8 cells by 8 cells with 0.4 and 5 millimeter strut diameters respectively. Similarly, sample number 23 and 24 consist of 10 cells by 10 cells by 10 cells with 0.4 and 0.5 millimeter strut diameters respectively. The table at the bottom compares experimental and analytical obtained lattice strengths. Here we believe analytical formulation provides reasonable results, only except for sample number 24. And we are not sure what causes this large error, considering the fact that experimental and analytical results are in agreement for the other 3 samples, sample number 21, number 22, and number 23. Finite element simulations are performed using Abacus software. In the simulations, elastic, perfectly plastic material is utilized with a Poisson ratio of 0.3, Young's modulus of 70 gigapascal, and yield strength of 460 megapascal. Only sample number 3 is considered in the simulations, and 10 elements are attained in each beam, and 2 node linear beam elements are utilized. Also, a friction coefficient of 0.1 is utilized for contact interaction. As stated in the previous slide, multiple finite element models are considered in numerical investigation. What we mean by multiple finite element models is that we utilized single lattice, double lattice, triple lattice, quadruple lattice, quintuple lattice, and decouple lattice models. Here, single lattice corresponds to 1 unit cell along each principal direction. Double lattice corresponds to 2 unit cells along each principal directions. Triple lattice corresponds to 3 unit cells along each 3 principal directions, and so forth and so on. What we see in this slide are single lattice, double lattice, triple lattice, quadruple lattice, quintuple lattice structures. Here, undeformed structures are shown in white color, whereas blue colored structures reflect deformed shapes. We first validate the analytical solution through finite element simulations. We run 2 simulations with 2 different beam lengths. Beam lengths are chosen as L equals 0.866 millimeters and L equals 1.732 millimeters. And we name them as half-length single lattice model and full-length single lattice model, respectively. Those lengths are chosen to be consistent with sample number 3 of cubic vertex centroid configuration, which has a beam length of L equals 1.732 millimeter, and whose cell in each principal direction A equals 2 millimeter. Please note that finite element results given in this slide, this one, shows undeformed and deformed shapes of full-length single lattice model. The table at the bottom compares analytical and finite element results of half-length single lattice model and full-length single lattice model. As can be seen from the table, the difference between analytical and finite element results decreases as the beam length increases. This is an expected outcome as the analytical model is based on beam model. In other words, analytical model would provide more accurate and reliable results when the beam length is much larger compared to cross-section diameter. Please also note that collapse load in numerical simulation corresponds to maximum force experienced during simulation. In addition to two different single lattice models, we performed finite element simulations for double lattice, triple lattice, quadruple lattice, quintuple lattice, and decouple lattice models as well. The results of these simulations are presented in the table here and in the figure at the bottom right here. As can be seen from both the table and the figure, plateau is reached around quadruple lattice model, which consists of 4 cells in each principal direction. Here, the coupled lattice corresponds to sample number 3 of cubic vertex centroid configuration, in which the numerical strength is obtained as 7.28 megapascal, and the experimental strength is obtained as 35.5 megapascal. The huge difference between these two results suggests that 2D finite element models may not provide accurate results. Hence, 3D models need to be utilized for more accurate and reliable results. On the other hand, 2D finite element model captured the shear bands, which is displayed here at the bottom center of the slide. The whole decoupled lattice with undeformed and deformed shapes are shown in the slide as well, and can be seen at top right. As two-dimensional finite element model does not provide consistent results with the experiments, we investigated the contribution of shear effect on this inconsistency. The investigation is conducted using a simple case, a circular cylindrical rod with a fixed end and a free end, where the force is applied. The limit analysis for this straightforward case results in a collapse load of 4 times sigma y r cubed divided by 3L. Here we utilize a rod length of 1.732 millimeter, a circular cross section of a radius of 0.2 millimeter. Again, these dimensions are chosen to be consistent with sample number 3 of cubic vertex centroid configuration, which has a strut length of L equals 1.732 millimeter and a circular cross section of a radius of R equals 0.2 millimeter. As the analytical model is based on beam model, beam element utilized in 2D finite element simulations to be consistent with analytical development. The analytical results, as well as 2D and 3D finite element results, are given in the table at the bottom right here. Here, numerical collapse loads, these two, correspond to experienced force values at 0.5 millimeter vertical force. Correspond to experienced force values at 0.5 millimeter vertical free end displacement. As can be seen from the table, analytical result is in agreement with 2D finite element results, which is expected since analytical model is a two-dimensional model as well. However, 3D finite element result differs much from both the analytical result and the 2D finite element result. And this outcome suggests the use of three-dimensional finite element model to accurately represent the experimental cases. Although we have started performing 3D finite element simulations, all simulations have not been completed yet. We only conducted 3D simulations for single lattice, double lattice, and triple lattice structures of sample number 3 of cubic vertex centroid configuration. Hence, there is still much to do in this regard in future. The one shown in the slide here at top right, by the way, belongs to finite element simulation of a double cell structure. There is also more work to perform in experimental part of the research. Our aim is to conduct additional experiments of same configurations, but with larger strut length to strut diameter ratios. This investigation will help us to examine the accuracy of analytical model better, since the shear effect would turn into be negligible as the strut length to strut diameter ratio increases. Thank you for listening.